All right, so hello everyone. Welcome back to your Comp 335 tutorial. So before we get started, I just wanted to go over some housekeeping things. So as you all probably know, assignment 3 is due tonight. So make sure you've submitted that by 6 p.m. The other thing is, like I said before in the last tutorial, we're getting closer and closer to the end of the semester. So technically, next week is the last week. So again, keep that in mind and try to manage your time. And then the last thing is, I just wanted to know, since I don't actually have access to this, does anyone have the date of the final exam? 29th of June. So that's a Tuesday. Okay. All right. So I'm asking so that I can plan a review. So if it's the 29th, then I'll think of something before that. So thanks for the information. Okay, so that's for housekeeping. So now let's actually move on to the material of the tutorial. So in this tutorial, we'll be looking at the focus of last lecture, which is Pushdown Automata. And we probably won't have time, so I'll probably post a recording for going from a context-free grammar to a PDA. Note that it was seen in class that you can go from a PDA to a context-free grammar, but this is not tested, so you don't need to know this for an assignment or for the final exam, but you do need to know the context-free grammar to PDA algorithm, which is actually probably one of the simplest algorithms in the class, so that shouldn't be a problem. Okay, so the focus of today really is just going to be PDAs. So what is a PDA? So let's just take a step back and think of the automata that we've seen so far. So far we've only seen two types of automata. We've seen finite automatas. So we've seen deterministic FAs, so DFAs, and we've seen non-deterministic FAs. So, and we saw that the languages accepted by DFAs is equal to the languages accepted by NFAs, which is equal to the set of regular languages. Okay, so if a language is regular, then it has a DFA that accepts it, and if a DFA accepts a language, then that language is regular. Okay, so that's finite automata, and so what was the limitation? The main limitation of an FA was that it was essentially memoryless. So why do I say that it was memoryless? Because if you have a transition like I have Q1 and then Q1 reads A and then goes to Q2. So imagine that you have your input tape and at a certain point you're reading A. So that allows you to go from Q1 to Q2. What happens is that once you transition to Q2, the only thing you remember is the very last thing you just read, right? So essentially you can't remember anything about the previous input per se, right? So that's what I mean by memoryless. So it just means that the memory size is actually just one. It's the last thing that you read. You can remember that, but you can't remember anything else. Okay. So this was a limitation because, for instance, if you have a language like AN, BN for n greater or equal to 0, then the idea for accepting this type of language is that you need to ensure that the number of A's is the same as the number of B's, right? So what you need to do is you need to actually have a memory of size n, because once you have a memory of size n, then you can remember n consecutive A's, and then check that there are, so for instance, if n was 7, then you could check that there are exactly 7 or n consecutive B's, right? So this is just for the sake of example. And of course here n is arbitrary, right? Really, it's an arbitrary number. So that means that to create a machine that accepts a and bn, you need to create or have a structure where you can essentially store an arbitrary amount of memory. Okay, so arbitrary amount is not the same as infinite. So in PDAs, which we're going to see in a second, you do not have infinite memory. That's impossible. Nothing has infinite memory, but you have an arbitrary amount, an arbitrarily large amount of memory, which is not the same as it being infinite. Okay. So so that's the idea. And so the way that we're going to implement this memory, so what is our memory data structure going to look like? It's just going to be a stack. Okay. So a stack, if you've done 352, is a very simple data structure where there's essentially only 2 operations that you can, well, there are a few more, but the main 2 operations on a stack are popping and pushing, right? So if you have a stack which has, let's say, 1, 2, 3, this is the bottom of the stack. So from now on, I'm going to use the $ to signify the bottom of the stack. Then you can either pop the top of the stack. So you can either pop it, meaning you remove the top element. So remove the top element, or you can push something on the top of the stack. So let's say 4. So push means place at the top, okay? And so this, this additional memory that we're going to introduce is going to create a PDA. So it's a push-down automata because you're pushing and also popping. So that's why it's called that. And this is going to allow you to increase the set of languages that you can accept. Okay, so let's look at a formal definition. I won't go too much into detail, but a push-down automata, or in this case, what we'll be looking at is non-deterministic push-down automata, so NPDAs, are defined very similarly to NFAs or DFAs as a 7-tuple. So you're going to recognize a lot of the same symbols as in DFAs. We're just going to have to introduce a few more which are related to your stack, okay? So you're still going to have Q, a set of states, sigma, an alphabet, a delta, a transition function, Q0, a unique initial state, and F, a subset of Q, a set of final states. But to that, you're going to be adding an alphabet for your stack, so your stack alphabet. So in other words, the symbols that you can push and pop to your stack. And you're going to have a stack start symbol. So sometimes we use the $. You can also use Z, really it doesn't matter what you use. And really the start symbol is just there to indicate the bottom of the stack. Okay, so that's the main purpose. And in fact, it's a very important purpose because you need to know that you've reached the bottom of your stack when you're pushing and popping things. Okay, so let's look at an example of transitions that you can see in a PDA. Okay, so in a PDA, your transition function is slightly more complicated than when it was for FAs. And the reason for that is because your transition needs to account for the change in the top of the stack. So how do we do this? Well, suppose we had just, let's say, created a state in your PDA. So this is just any other state that you would see in any type of machine. And we have these two transition functions, okay? So what do these transitions say? So they're telling us two things at the same time. They're telling us that if A is on the input tape, so if you're reading an A, so imagine you had a string that you were reading, so you had read a part of that string and you had gotten to A. So let's say you have a pointer at A. So it's saying that if you're in Q1, right, and you read an A on your input tape, and you have on your stack a B. So B here, this B here means that B is at the top of the stack. So then this is saying that if you're in Q1 and you're reading an A and B is at the top of your stack, then transition to Q2 and replace B with CD. So, and what's important is that here the leftmost symbol, so in this case C, should be at the top of your stack, okay? Meaning that if you take, so if you were to take this path, then your stack would change from, I don't really care what's under the B for now, but you have a B at the top, then the B gets popped and you push a D and then C. So you push D and then C. And now you're at Q1. Okay, so that's how you read this type of transition. So that's for sort of this edge. How do you read this edge? Here we have an interesting string or symbol here. We have the lambda or the empty string. So what does it mean if the empty string is in the stack transition? Well, it's not very sort of complicated. What this is saying is if you have, again, in your input tape an A, right? So you're reading an A, and at the top of your stack, you have a B, then the other possibility, so in fact, this is non-deterministic because you have two choices. And so the other choice is you can take this B, you can pop it, and then push a lambda, right? But pushing a lambda means that you haven't really pushed anything. So it could also just be equivalent to writing that you have the same stack content after B and then nothing instead of B. So basically, when you say B is replaced by lambda, this just means that you're popping B. Okay, so that's for popping B. The last very important sort of stack operation that you'll see isn't actually here, but let me add it. So if you read an A, actually I think blue is a bad color. Let's do, yeah, let's do green. So if you read an A and you're not very concerned with what's at the top of your stack, and you're going to replace that thing that you're not very interested in, so in this case the lambda, with let's say a D, then this just means that you don't care what's at the top of your stack. So for all you care, for all intents and purposes, for this example, you don't really care what's in your stack. You're just looking at the potentially next element of your stack, and you're saying, okay, what I'm going to do is there's nothing here at the moment. What I'm going to do is I'm just going to add a D to that, to the top of your stack. So then this just translates to pushing D. Okay, so now there's basically three main operations. You can basically do an intermediate, sort of do many things at once. By here, you're popping a B, you're pushing a D, and you're pushing a D. Or you can do sort of atomic operations where, in this case, you pop a single B or you push a single D. Okay? And that's the mechanism. That's the mechanism, and really all you need to understand to sort of know how a PDA works. Okay, so that's the mechanism of how this machine works. And if you just want to write it mathematically, here, because it's a non-deterministic choice, here what this is saying is, if this is your state, this is your input, this is your top of the stack, then there's two possibilities. Either you can go to Q2 and replace the top of your stack with CD, or go to Q3 and replace the top of your stack with lambda. Okay, so this is what this means, and this is how this translates to something like this. Okay, so that's for understanding how a PDA works. All right, now I won't go too much into detail with this because it's gonna just take a lot of time because it's a theoretical concept. But basically, there's this thing called an instantaneous description, which allows you to sort of completely describe the state of your stack at a specific instant. Okay, and the way it's read is it's read as a triple, and it tells you what state you're currently in. So your current state is Q. What is left to read? So what is the unread part of your string? And what is the current content of your stack? Okay, so if you have these three things, then at a given instant, you know exactly what's going on in your machine. Okay, and so this is useful because it allows us to define what the language accepted by a PDA is. So the language accepted by a PDA M is just the set of all strings such that if you start at Q0, you have W to read and you have Z at the top of your stack. Then in 0 or 1 more moves, you can go to a final state P. So in this case, P is part of the final states. You finish reading your string and you don't really care what is in your stack. So the final stack content for a string to be accepted is irrelevant. All right. And maybe one more thing actually is so this is true, except there's a single exception, is that your stack cannot be empty, let's say mid. So mid, by mid, I mean during mid computation. Okay, so meaning that if you have, let's say you have your machine and you have your state here. So you have a state here, Q, and you have, let's say, A, lambda, lambda, okay? And that goes to P, right? So lambda, lambda, what does that mean? That just means that you don't change anything to your stack, right? So if you're in Q and you're reading an A, but if your stack is empty, so let's say you have an empty stack, so somehow the person who designed this PDA didn't correctly manage memory, and so you're left with an empty stack, then this transition can't proceed even if you have lambdas, because your PDA essentially can't continue a computation if its stack is empty. That's just a rule that you find in PDAs. Okay, so that's something that's important to remember. Okay, and so in general, that's the sort of theoretical aspect of PDAs. Okay, so I've been doing a lot of talking. Maybe you're confused, and if you are, it's normal. So let's actually look at a concrete example. So we have to start off a more or less simple PDA. And this PDA, I'm claiming, accepts the language. So if this PDA is M, then I'm claiming that L of M is AM BN for M greater or equal to N. So in other words, you have more A's than B's, right? Or you have more or an equal number of A's than B's, right? So that's what that means, okay? So why is this true? Well, let's just look at an example computation, okay? So suppose your input string was AABBB. So in theory, this should be rejected, right? Because you have 2 A's and you have 3 B's, and 2 is not greater or equal to 3, and so this should be rejected. So let's see if that happens. So your input is AABBB. You can assume, so here, the assumption, we're assuming that the $ is already at the bottom of the stack. So this is a fair assumption. You can, in your assignment, assume that you have the $ at the bottom of your stack. Or if you want to be sure, what you could do if you just want to sort of be safe, but this isn't necessary, is just push. So you're not going to read anything, but you're going to push a $ at the beginning. So this step is not necessary. But sometimes it helps. I mean, it helps me just to make sure that I know that what I'm saying is that the $ is at the bottom of the stack, but it's not sort of, you're not obliged to do that, okay? So let's just say that the assumption is that we have the $ at the bottom of the stack and that your initial state is Q0, right? So you're starting at Q0 and you're going to read A2, B3. So imagine your stack is here, right? So you have your $ and you're going to read AA, B, 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 right? So you start here at Q0. So I'm at Q0. So I can use this transition here, which tells me that if I'm in Q0 and I read an A, it doesn't matter what's at the top of my stack. I'm just going to push an X. So I'm going to push an X whenever I see an A, right? So I'm going to push one X, and that's going to allow me to go to the next symbol, right? So I'm going to move my pointer to the next A, but I'm still going to be in Q0, right? And again, I'm going to do the same thing. I'm going to read an A. I don't care what's at the top of my stack. I'm going to add an X to that. So really what that means is, again, I'm going to push X. So I'm going to push another X, okay? So now that sort of finishes reading my A's. So now what happens is I'm technically still in Q0, right? So I've gone back to Q0. And now I'm reading a B, okay? So I'm reading a B. There isn't a transition here for a B. So what I'm going to do is I'm going to use this lambda transition. I'm going to use this lambda transition to go to Q1, right? So the Q0 becomes Q1, but I haven't read anything, right? Because remember, lambda just allows you to go, it allows you for free. So it allows you for free to go from Q0 to Q1, okay? And no, it doesn't matter. X it didn't need to be X. It could have been Y, or it could have been an emoji. So it wouldn't matter as long as you're using something as a counter. Okay, but good question. So for free, you're going to Q1, right? And now you're going to start reading your B's, right? So I'm going to use this transition. So what does this transition do? It essentially, right, so if you look at it carefully, it just says that if you're reading a B and there's an X at the top of your stack, you need to pop X, right? That's what it's saying, okay? So that's what I'm going to do, right? So I'm going to read this B, right? I don't know why I changed color. I'm going to read this B, and by doing so, I'm going to pop this X out, okay? So I'm going to pop this X. And so by doing that, I go back to Q1, right? Because the actual transition is telling me to go to state Q1. So Now I'm in the next B. I'm still at Q1 though, okay? And again, I'm gonna do the same thing. I'm going to read Q1, right? I'm going to, from Q1, read a B. And since X is at the top of my stack, I'm going to put pop another X, right? So now I'm at Q1, right? So again, I'm still at Q1 and I'm reading a B, but now the problem is the dollar sign is at the top of my stack, right? And I don't have a transition. I don't have a transition for when I have the dollar sign at the top of my stack. So this is very similar to when you had, like, let's say an NFA. Let's say you read an A, you got to this state of your NFA. Let's say it was a final state, but you still had more to read. If you still have more to read, then your even though you finish in a final state, this isn't considered an accept. It's a reject. Okay, it's a reject because similarly, so here it's a reject, and it's also a reject here because you don't finish all your inputs. Okay, because if we go back to this definition, here it says that you start with Q0, W, and then something in, so let's say the start symbol in your stack, and you transition, so with 0, 1 more steps, you transition to a final state, and you have nothing to read. Okay, so this definition is very good because it really encompasses exactly what an accept looks like. Okay, so that's why if we go through this computation and yada yada, we go here, we get stuck. And so AABBB or AAB cubed is rejected. Okay. And so I don't have an example for when it's accepted, but let's say, let me quickly show you one. So let's say I was reading AAB. So this should be an accept, right? Because you have 2 A's and 1 B. So if you start with the dollar sign at the bottom of your stack, so you read an A here, so you push an X. Then you go to the next A with Q0, you push another X. Then you go to Q1 with B, you pop your X here with the B, and you're still in Q1, but now you're finished your input. Again, it doesn't matter that your stack still has some things. What matters is that you finished your input and you're at a final state. Okay, and so this that's why this leads to an accept. Okay. Any questions about this? All right. So let's see if this was well understood. We're given the following transitions, and assuming that you have your input tape and you're reading an A. So assume you're at Q1 and you're reading an A. What should be the content of your stack after each of these operations? Okay, if you're given this initial stack content. Okay, so I'll give you a minute to try this out, and we'll look at it together after. So let's look at this exercise together. So again, like I said, we were assuming that we started at Q1, we were reading an A, and each of these were different stack possibilities. So for each of these, what is going to be the content of my stack once I use this transition, okay? So for the first transition, you can just imagine that you're at Q1, that you're reading an A, you don't care what's at the top of your stack, and you're replacing that with C, okay? So what that means is that you're just pushing C, right? Meaning that if you have a $sign and you have a B, then what you're going to do to your stack is you're going to push a C at the top, okay? So the content of the stack is now CB, okay? The next one here was a pop. So in this case, you were at Q1, you were reading an A, you had a C at the top of your stack, and you were popping that. So of course here, I would need to have a C at the top of my stack. And so because I do have a C at the top of my stack, what I can do is I can use this transition to replace C with lambda. So in other words, pop C. And so the content of my stack is just B $sign. Okay, so it's B $sign. Okay, so now another example, which looks like a lambda transition, but not quite. So in this case, you have a Q1, you're reading an A, you don't care what's at the top of your stack, and you're not replacing that with anything, and you're going with to Q2. Okay, so what does that mean? That means that your stack is unchanged, right? Your stack is unchanged, so you don't change anything, you still have CB. Okay, and there's a good question. There's a very good question, which I was actually about to ask, is if, for instance, you had, let's say, a Q1, A, C lambda, Q2, but you didn't have a C at the top, you had a B. Then what would happen is you would essentially just be stuck. You would be stuck at Q1, okay? Because to move forward from Q1 to Q2, you need both to be able to read. So this, you need to be reading an A, and you need to be having a C at the top of your stack. Okay, so would it cause, so yeah, in this case, because you're stuck at Q1, then this would naturally lead to a reject because you can't kind of move forward. So then yes, so that's a good question. Okay, and then the last one here was if you're at Q1 and you're reading an A, you have a $sign at the top of your stack and you replace that with lambda. Then what happens if your stack is just a $sign? Well, here, this is allowed. So this is allowed. And the content of your stack is just going to be empty. But once it's empty, so once you're at Q2, you can no longer have any more transitions. So let's say if I had lambda, 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 then this is disallowed, so not allowed. Because empty stack. Okay, so just make sure to remember that. All right. Okay, so hopefully I've talked enough and annoyed you enough so that PDAs are a bit more clear in terms of their functioning. So now let's actually look at designing a PDA. Okay, so for this first one, I'm not going to do all of it myself. I'm still going to let you do it. I'm just maybe going to give you the idea. Okay, so what's the idea here? The idea is, so of course we want to give a PDA. Okay, perfect moment for OneNote to stop working. Okay, give me 2 seconds. Sorry about this, guys. Your screen, share. Okay. All right. Okay. Sorry about that. So what's the idea here, right? We want to give a PDA for the language L, where we want to accept the language of the strings AI, BJ, CK, where A, I plus J, so in other words, the number of A's plus the number of B's is equal to the number of C's, okay? So what's the idea here just in terms of stack? So very high level, what's the idea is if you see an A or a B, you're going to push, let's say an X. So you're going to keep pushing X's. And then if you see a C, you're going to pop X. And at the end should have a stack that looks like this. So assuming that we start with a stack that looks like this, then what should happen is, let's say you have A, B, B, C, 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 C. What should happen is you're going to read the A's, push X's, read the B's, push X's, and then read the C's and pop for each X. So for each C, for each C and X you see, you're going to pop it. So you're going to pop this guy, this guy, this guy, and this guy. So that at the end, what you're left with is just this stack. Okay, so that's the idea. So now I'll give you the chance to try it out. So design a PDA that essentially does that. Okay, so I'll give you a minute and a half. So let's be a bit generous here. Okay, so let's look at this together. So again, what's the idea here? The idea is, let's say you have something like, so I'm going to reuse my example, A, B, B, C, 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 C. Then you have to read A's, right? So let's do something. Let's just add the $sign to the stack. So in this case, I'm just going to, for the sake of concreteness, say I'm adding the $sign. Okay, so this isn't required, but let's just say here what I'm doing is I'm adding, I'm signaling that the bottom of my stack is a $sign. Okay, and now what I'm going to do at this point is I need to read A's, right? So it has to be A's, then B's, then C's, right? So this state is going to be used for AI. So I'm going to read A's, and then for each A that I read, I'm going to push an X, okay? So imagine here that you have two A's, then you're going to use this state and this transition to, so you're going to go to this state here, read an A, and by reading an A, you're going to push an X, right? And then go to the next state, read another A, and then push another X, okay? Then at that point, you're going to go to a new state for the B exponent J, okay? So I'm going to say this is for B exponent J, and so let's just say that I'm going to use lambda transitions. So I'm just going to use lambda transitions so that I don't waste input on my tape, okay? And just so that it's very clean what's happening at every single state, okay? So at this state, whenever I see a B, I'm also going to push an X, okay? So what does that mean? That means that when I go to this new state here, so when I happen to go here, I'm going to read this B, push an X, read this B, push an X. And then at that point, I'm done reading my A's and B's. Now I want to pop for each X and C that I see, for each C that I see, I want to pop one X, okay? So I'm again going to use a lambda transition to go to CK. And then for each C that I see, so let's say I'm here, I want to pop an X, right? So I'm going to pop an X. So that's what I'm going to do. For each C that I see, I'm going to make sure that I have an X at the top and pop it, okay? And so in theory, what should happen is that in theory, if I have the same number of A's and B's as C's, then what should happen is at the very end of this, this loop, I should have nothing in my stack. I should just have the stack, the bottom symbol, right? The stack start symbol. And so that's what I'm going to check for. I'm going to be able to go to my final state, I'm just going to say that I need my stack to have only the $sign. Okay, and that's how you would create a PDA. It's not, of course, the unique one, but a PDA to accept this language. Okay, so question. Let's start with Tabil. Is there a way to combine the two states for A? No, there isn't. No, they're not doing the same thing. Well, they are doing the same thing, but you need to respect the order. Because if you were trying to be lazy, well, I'm not saying that you're trying to be lazy, but like if you were trying to save states and you did something like A lambda X and then B lambda X, then what could happen is you could possibly accept something like AB, AB, C, 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 okay? Because then you could intertwine your A's and B's. So, so no, you really need to separate, you really need to keep that order there, okay? So then I think that answers just loop A and B over one state, so you can't do that. On the first one, just you're starting with an empty stack. Can't follow any. No, so you're not, so that's a good question. Here, the assumption is that your stack is not empty. So you're never starting with an empty stack, okay? You're either always starting with a stack that has the start variable, or what I like to think of it is just imagine you have main memory. Users are writing to main memory, right? And so what you want to do is you want to separate your program from the program of other people that are using main memory. So imagine it's a shared, a sequential main memory access. So it's not random access memory. So then to differentiate this block of memory with yours, you're just going to add a $sign. Okay. And so the idea is that you can't at any point go in a transition here and then empty back, let's say, empty back your stack. Okay. Because then you don't know what's here, right? You don't know what's underneath your start symbol. So that's how I see it. Okay. All right. But good questions, very good questions. Especially the combining one. So you just be careful about that. Is it good practice? So that's a good question. I mean, I think you can correct me if I'm wrong, but I don't think like in the slides in Shiri's slides, I'm not sure if that's what he does. I can't remember honestly, but it's not like required. So it's just as good to start off here, basically. So it's not really kind of like a best practice, like you would kind of say in like a general best practice. I just do this because for me it's more visual, and like I kind of remember for myself that I'm dealing with the $sign at the bottom, but it's not required. So yeah. Okay. So any other questions about this? No? Okay. So we're going to do another exercise, and this one I'm not going to give you the idea. I want you to think of what the idea is with the stack. So you want to accept the language of strings where your strings look like A2N, B3N. So in other words, let's say N is 2, then you can accept something like A 2 times 2, B 3 times 2, so A4, B6. Okay, but basically this needs to be 2 times N, and this needs to be 3 times the same N. Okay, so I'll give you a bit more time because you actually need to think of what the idea is with the stack. So let's say, what time is it? Let's say 2 minutes, maybe, let's say 2.5 minutes, give or take. Okay, and then we'll look at it together. All right, so let's look at this this exercise. So now for this one, what's the idea? Just in terms of the stack. Basically, it's for every 2 A's that you see, you're going to want to push an X, right? And so imagine you have, let's say, 3 times, so you have 3 pairs of A's, right? Then for each of these pairs, you're going to want to push a single X, right? So you're going to want to push a single X. So here you're pushing an X, an X, an X. So basically here you have 2 times 3, right? So 3 here is n. So n really is the counter for your stack. Okay. So then what you're going to want to do is for your B's is then for every 3 B's, you're going to want to pop an X. Okay. So then because if n is 3, then you should have exactly 3 times 3, 9 B's, right? So you should have 3 times 3 B's, right? So you should have once B3 to pop 1X, another time B3 to pop another X, and then last time B3 to pop the last X. Okay, that's the idea. So then how do you do this? How do you do this? Well, okay, so this time, let's change it up. Let's assume, again, it doesn't really matter which one you pick, but this time, let's assume that I already have the $sign at the bottom of my stack, okay? Then what I can do is I can use a pair of states for a loop that's going to consider pairs of A's, right? So let's say I read an A here, then I'm going to push an X, and then I'm going to read another A, not going to touch my stack, but essentially what I've done is reading these 2 A's, I've pushed 1X, okay? So then if I have 3 pairs of A's, then I'm going to go through this loop 3 times, right? So I'm going to go through it once, twice, 3 times. So then I'm going to go through this guy 3 times. So I'm going to push X 3 times. You can also, yeah, exactly. You could also do lambda lambda here, and then lambda X here. So it wouldn't matter, okay? So then once you're done doing that, once you're done pushing your A's, your X's for your A's, then you can go to, you can go to, so this is for your A's, so A to N. Then you can go to your B's, so B3N. And essentially you're gonna do the same thing, but for each triple, so for each 3 B's, you're gonna pop an X. So let's say you read a B, you see an X at the top, you're gonna pop it. Then you read another B, you're not gonna change your stack. Then you read another B, you're not gonna change your stack. So at the end, what's going on is that for 1, 2, 3 B's, you're going to pop 1X. So then if you have 9 B's, so if here you have 9 B's, then you're gonna pop this one, you're gonna pop this one, you're going to pop this one, okay? So then, and then what you expect is that at the end, you expect to have nothing left. So essentially you expect to have your $sign and to end in a final state, okay? And then this is your PDA for this language, okay? So for each B, you want to push 3 X's. Oh, I see. Yeah, that's a different way of doing it. Except that you can't do that because here, you can only read the top of your stack. You can't read 3 X's, right? So, so you can do that here, right? You can push anything you want. but you can't read anything you want because it's still just a stack. So, you know, like in data structures, you can only look at the very top or first element. Okay. Any other questions about this? We can push multiple elements, but we can only pop. Yes, that's right. You can only read one element at the time, but you can push multiple elements at once. Which in my head makes sense, right? Because if you would be able to pop multiple elements, then it's no longer a stack, because then you're actually able to see an arbitrary length down your stack. So then it's actually more like an array rather than a stack, right? So that's why. Okay, good question. Any other questions? No? Okay. So, so the next one, actually quite difficult to explain. All right, well, I'll still, okay, because I can already tell this is going to be difficult to explain, but you can try to think of the idea. Let's say just try to think of the idea for a minute. So you don't really need to sketch the PDA, and then we can look at the PDA. But just I'm warning you that this one's a bit more difficult to explain. Okay, so take a minute to think about it, and then we'll look at it. Okay, yes, very good. There's a very good idea in the chat. So so the idea here is you want to be able to remember how many A's and B's you had, and you want to be able to remember how many C's you have. And you want to be able to compare these two numbers so that let's say you have A, B, A, right? So your counter is let's say at 3. So your counter is at 3. Then if you have, let's say, 2 C's, your counter goes down. And you can only accept if you have a non-empty stack. So when I mean non-empty, I just mean you don't read the $sign, okay? So that's the idea, okay? But you have to notice something, is that you, in this case, can't just use a single symbol. So you can't just use one X. So you can't just do something like, oh, I read an A, so then I push an X. Because right, in this case here, doesn't matter what the order is. So then you can't do something like here, I have an A, I push X, I have a B, I push X, and I have a C, I pop X, okay? So why can't you do that? Because what if, and then like something like, oh, go to the final state if you have right? You can't do this because imagine you started with 2 C's, there isn't a transition for if you start with a C. So because C can come first, you need to have sort of 2 stack symbols. You need to have the possibility where you're going to start counting your C's. And then, so imagine you have a bunch of C's, and then you're going to, so imagine, let's say for C's, you had a Y. So let's say you had, let's say 3 C's. So you had 3 C's. And then you had, let's say, an A and a B. Then you would be able to say, okay, so now I'm going to take out the Y, I'm going to take out the Y. So when I read an A and a B, when I have a Y, then I pop it, okay? But if I start with an A and a B, so I have an X and an X, and I have a C, then if I have a C and I have an X at the top, then I pop it, okay? And let's say if I have, so now you can kind of think that there's a bunch of different possibilities, right? So you could have a $sign at the top of your stack. You could have a X at the top of your stack, or you could have a Y at the top of your stack, okay? If you read a C, so let's say you read a C, then what you're going to do is you're going to push a Y, let's say, okay? Because you wanna differentiate the Y's that you're reading from the A's and B's that you're reading. So for C's, you're gonna push a Y, but for A's and B's, you're gonna push an X, let's say, okay? So then that's for if there's a $sign at the top. So if you're just starting, okay? But now what if you've written, so let's say you've written a bunch of X's, and let's say in the next symbol that you read an A or a B. If you read an A or a B and you have an X, then you're again going to push an X, right? Because you're just continuing your pushing of X, okay? But if you read a C, then you're not going to push an X, you're going to pop an X, right? So because you want to decrement your counter if you have a C and you're reading an X, because the C is canceling out your counter for your A's and B's, which is X. And then the same thing for the other way. So if you have a Y and you're reading a C, then you're going to push another Y. If instead you have an A or a B and you have a Y, then you're going to pop a Y. Okay. So hopefully it's clear why you're doing this. And hopefully it's clear that because there's only 3 possibilities, right? You can only have the $sign, an X or a Y at the top of your stack. Then this is exhaustive. Okay. So then what we can do is we can just translate that to a single state where I'm just going to do exactly what I wrote here, but I'm going to translate it to transition. So let's say I have an A and I start with a $sign. Then don't do this, right? Don't do $sign replaced by X, because then you don't have a $sign anymore. So you need to do X $sign, okay? And the same thing for B, you have $sign, add an X to the top of your $sign. But if you have a C, then add a Y to the top of your $sign. Okay, so that's for this guy. Okay, then for this guy, we're just going to write the transitions for our logic, right? So I'm going to answer that question at the end, just so because I don't want to finish this thought here. But so let's say I read an A or a B, right? And I see an X. If I see an X, then I push an additional X on top of my X. Okay, so that's what I do. Okay, so so for instance here, let me think. Give me 2 seconds to. Okay, I'm trying to think at the same time. But okay, let me just keep going with this transition. So this is what I mean by push an X. Then if I have a C and I have an X, I'm going to pop it. Right, so this is for this guy. Okay, yeah, that's the answer I was looking for. Yes, thank you, Jonathan. So then the last thing here is just doing the same thing for C. So if I have a C and I have a Y, then I'm going to push another Y. But if I have an A or a B, I'm going to pop it. Right? Okay. So then, yeah. So the question was, if you put, why can't we just do lambda x, right? So yeah, if you put a lambda, then you can always use it, right? So lambda is going to work for the dollar sign and for this guy and for yeah, so I'm trying to formulate this in words, but I'm having a bit of trouble. But it seems like Jonathan's explanation was good enough for Tahar, so hopefully no one else has the same question. Because basically the idea is once you're done doing this computation, then with a lambda, you make sure that you have an X at the top. And let's say it doesn't really matter what you do with your X, or you have a Y at your top, and then you finish in a final state. Okay. So then this would allow you to use a counter for your A's and your B's. And then would make sure that you either have more A's and B's than C's, or more C's than A's and B's. Okay, so that's the idea. Okay, so any questions while I think of? Yeah, so any questions about this? All right, okay, yeah. Okay, I think I just realized why. Okay, because if you have something like A lambda X, then basically this is saying that whatever you have at the top of your stack, you're gonna push an X, right? So then even if you have a Y at the top of your stack, you might still push an X. And that's not the behavior that you want, okay? So that's what Jonathan was saying. I just couldn't formulate it. All right. Any questions about this other than that? No? Okay. So that's the conclusion of the tutorial. Like I said, I'm gonna post a recording for this. So yeah. So if there are any questions in general, now I can take them. I know that someone had a question about the previous exercise. I mean, it is 5:25. So, oh, you mean that's it for the PDA? Yes, that's it. And for the tutorial, I mean, it is almost 5:30. So yes, that is it. But like I said, I'm gonna post something for this. All right. So I think Nabil had a question.
Yeah. Hello?
Yes.
Hi. So yeah, I just have a quick question on slide 16.
Yes. Yes.
So why is it that you didn't just make Q4 the final state instead of having like if your input's a lambda and you see a dollar sign in your stack, then go to Q5. Like, why didn't you make Q4 the final state?
You mean you wanted to say, let's say, go here and then add this here?
No, like like I guess I'm not understanding like what the final transition is doing exactly.
Oh, okay. Yeah.
Because
So yeah,
I also like when I drew out the PDA, I made Q4 my final state. I just like kept popping off an X for if
right.
I saw a C in my input, right? And
But
then
how do you know when to stop popping? Like, because if you have just something, whoops. Sorry, because my OneNote
yeah,
again
yeah,
isn't
no
working.
worries, no worries.
But if you, so the idea is if you, let me think about it for a second. If you keep popping your C,
Hmm.
um, so
Could it
why?
be like if you have less C's than A's and B's, then like it would be in like Q4 is your accept state.
Yeah. That's what it is. That's
Okay,
exactly what it is. Yeah, because
okay.
so you might be able, like, let's say you had A, B, what is it? What does it have to be? Let's say C.
CC, yeah, yeah,
So
exactly. I
that
see.
so then if you just had this
Hmm.
and this was a final state, then you could accept this guy.
Okay,
You,
which is wrong.
yeah, yeah.
Okay,
So
okay.
this is making sure that um, you you have you've popped the same number, like you've pushed the same number of A's and B's as C's.
Okay. And then what's that last transition doing? Like if you see a lambda on your input string, you replace the dollar sign in your stack with lambda, which is just popping. Does it pop or not
Yeah,
even? It just like keeps the
yeah.
dollar sign in the
No,
stack.
this is popping the dollar sign, but you could also just do dollar sign. It doesn't
Oh,
really
okay.
matter.
Oh, okay, okay, got you. Got you.
Yeah,
Okay. Okay. Sounds good. Thanks.
yeah, no problem. All right. Any other questions? No. Okay. So so yeah. So thanks for attending. I don't know. I was going to say something else, but um, and yeah. So have a great weekend, everyone, and I'll see you Monday. Bye bye.